Hey everybody, welcome to this video, and we're going to be talking about gravitation today. So gravitation, what is it? Well, I'm going to start out here by defining the gravitational force, and I put a few extra words in here just to emphasize the meaning of this. So first of all, when you have two masses in the presence of each other, and I put in here not at infinity because infinity is important when we talk about defining potential energy. But if they're not at infinity, okay, and they're in the presence of each other, they exert an equal and opposite attractive force. So attractive force on each other known as the gravitational force. So this is what Newton discovered, and he discovers that this force varies as an inverse of the square of the distance between them. So when I have my two masses here, I draw a circle here just to show that there's a mass, but we're really referring to the center of mass here, which I'll draw as a dot, and then this is mass 1, and I'm going to have mass 2 here, which I could do in a different color. I'll do that one in green. I have mass 2 here, and of course we're talking about the center of mass here. Now, when we're talking about the radius, we're actually talking about the distance between the two centers of mass. So we're talking about from here to here, which is important to note because later on, when we start talking about going into the Earth, that's going to change. Or if you're on the Earth, the radius is going to be the distance from you to the center of the Earth. Or if you're on a satellite, it's going to be the distance from the radius of the Earth to the altitude of the satellite. So it's just important to note these things. Now, when we do the notation on this is a standard notation to say that you're getting an equal and opposite force. So when you have mass 1 here, you say the force on 1 from 2 equals the force on 2 from 1, and they're equal and opposite. So you're just showing that they're going back and forth in equal and opposite directions like this. And so another way to say that is the force on 1 from 2 equals the negative of the force on 2 from 1. And that's just another statement of the third law. So how does Newton's law work? Well, we have to write out the equation here with the negative sign. Now I want to emphasize what this means. This is important because the negative means that we're talking about an attractive force. So when we're talking about free body diagrams, we don't include the negative, but that is just to show you that it's attractive. Just like when we talk about Hooke's law, if I say F equals negative kx, I'm saying that that's a restorative force always pointing towards equilibrium, and that's what the negative means here. But when we do the free body diagrams, we don't include the negative with Hooke's law either. So just want to emphasize that. Now there's a new g here, a new gravitational constant. It's 6.67 times 10 to the minus 11 newtons meters squared per kilogram squared. M1 is mass 1, M2 is mass 2, and like I said before, R is the distance between the centers of mass. Now, this equation here, I wrote M1, M2, okay? And there's nothing wrong with that, but usually what you'll see with these equations is you'll see G, and then they'll have big M like this, little m over R squared. And the idea there is that if you have one mass that's much bigger than the other, like a planet, that's going to be the big M here. So that's important when we're talking about satellites or we're orbiting or we're trying to escape the Earth with rockets, that this big M is usually the notation that we're going to use. Now you might also see the equation written in unit vector form. So G M1 M2 R squared and then times R hat. And remember, the unit vector is just a vector that points in the direction of the force and has a magnitude of 1. So when we're talking about x, y, z, remember that when we have our components, we just use I, j, and k to emphasize that that's in the direction of each of these components. When we're talking about the gravitational force, though, that radius could be on any axis. So if you have x, y, and you have z coming out like this, if I just have some odd radius like this, that gravitational force of attraction that we talked about is going to be in the direction of r hat, which is pointing in this direction, magnitude of 1 pointing in that direction. So pointing in the direction of r, magnitude of 1, it's not going to affect the magnitude of this, it's just going to give it a direction. So that's the idea with that r hat. So if you see that, that's all that means. It doesn't really add an extra r into the equation. It's kind of confusing. It looks like it's adding an extra r, but that's not doing that. Now, gravitational field is important because a single mass by itself creates a gravitational field very similar to how a charge creates an electrical field around it. The difference is that the gravitational field is always attractive. Now, we're going to get into nuances here in this chapter, and this chapter is really about bringing everything together that we've done throughout the year and bringing slight changes to everything. So first of all, when we see that we have f of g is g m1 m2 over r squared, this first part of the equation here, which I'll put a big M just to emphasize that we're talking about the Earth or a planet, gm over r squared, that's going to be called the gravitational field known as a sub g. So that arrow should be above the A, and it's at the surface. That's the gravitational field at the surface of the Earth. Now, that's not the same thing as G, which we'll talk about later. G is affected by other things such as the unevenness of the surface of the Earth, how far away you are from the center of the Earth, and how fast the Earth is spinning. So that's a nuance. But I'll just use AG, A of sub G there, just to emphasize that. So, what does it look like when you have a mass just by itself? Well, typically, if you have a mass, it's just sitting there and it's creating a field. You only need one mass to create a field. You see that right there? One mass to create a field. And that field is going to vary as a function of 1 over r squared. Now, so a sub g is going to vary as a function of 1 over r squared. Now, here comes alpha again. We've used alpha to talk about angular acceleration. I know it's confusing, but that's just to say it's proportional to or directly proportional to 1 over r squared. Sometimes we say proportional to like this, so maybe that's a better way to put it, but that's what I mean by that. I'm not saying angular acceleration. I'm just saying it's proportional to 1 over r squared. So if we have a graph, and we have my r here, and I have my ag, that is going to rise as a function of 1 over r squared. It's going to spike up as I get really close to that mass. And so why is that important? Well, if I represented this by arrows, like if I drew my field with arrows, I guess we'll use dark blue here, that as I'm closer to this object, those arrows, which represents the strength of the field, should be larger because the field is larger. Remember that as I'm closer to that object, the field is high. And then as I get away, the field starts to drop off very quickly. You see that right there? Drops off very quickly, asymptotically, right? So the only way that we can get a zero field is to infinity. And that's what I talked about before, because when we define the potential energy of a particle, we're going to take that particle to infinity. We're going to integrate that and take it to infinity. And that's how we're going to define the potential energy later on. But that's why these arrows vary in size. So as you get closer, the intensity of that is going to increase. Now, also one of the things to keep in mind that the intensity of a field, which we're not going to talk about too much here, because this is more of an electricity concept, but visually, the way that you determine an intensity of a field is if you drew a circle like this, the number of lines, and you can do it with your hand, you can make like an OK symbol and put it over, and you look through it like it's like a looking lens. The number of lines that you count is the strength of the field. So I count 1, 2, 3, 4 lines here, but if I do that same circle, let's just, hopefully that's the same size, not really, but let's just pretend, then I only count 1, 2 lines out here. So that's just like a visual way to look. If I'm looking to see the strength of the field, that's why, that's how you can determine how strong it is. So just a visual concept there with the field. And that's way more important with electricity. And they don't really talk about that too much here in this chapter, but it's just something to be aware of. So if I'm talking about the gravitational field, the concept is that if you have a field and you place another mass, then you get a force. So field and a mass, you get a force. Just like electrical field and a charge, you get a force. But this force is always attractive. So the force of gravity equals the acceleration of gravity. And I had changed this from G before because I was trying to clarify this. So that's why the G looks a little big, but AG times the mass. And if you put all these numbers in, and this is the gravitational constant 6.67408 times 10 to the minus 11 times 5.972 times 10 to the 24 over 6.371 times 10 to the 6. That should be squared. You'll get 9.8196 at the surface of the Earth. Now, why did I draw a point here and not a mass? I just drew a point, a dot. I could put a dot out here, could have put a dot out here. Why did I just draw a dot? And the reason is because it has nothing to do with the mass, the second mass. It has to do with the big mass. Remember the equation that the A of G is going to equal G big M over R squared. That's it. Okay, so this second mass has nothing to do with it. So if I'm just measuring the field, I'm just doing a dot. There's no mass. Okay, now A sub G does not equal G, which we'll talk about more later. They're not the same thing, but they're close. But this chapter is important to talk about why they're different. So this next example, I actually calculated what about a space station? Like the space station that orbits the Earth, what's the acceleration of gravity of that? I mean, people are floating around there. Shouldn't it be near zero? I mean, you would think that, right? But when you actually calculate it out, you actually get a number of about 8.66. Now, why is that important? Well, it's pretty close to gravity. If you divided that, if you want to find the number of G's, okay, you guys have heard that before. How many G's is something doing? A G is the multiple of gravity that you have. So if I'm experiencing 3 G's, then that's 3 times the weight of gravity. Typically, if you're experiencing 3 G's, you start to pass out. So if I divide that acceleration of gravity divided by G on Earth, I get 0.88. So you're still experiencing 88% of your acceleration due to gravity in that space station. So why do you feel weightless? And the reason is because you're in orbit. Now there's a lot going on in this question. The number of G's, by the way, is really interesting because when you are going up, you're much more susceptible to passing out. So let's say that you're here and you're experiencing G's. And so what's going to happen is, let's say you're going up in a space station. So your body's going to go up and your blood has an inertia and it's going to try to stay where it was. So what's going to happen is as you go up, your blood's going to try to stay where it was. And so it's going to have the effect is as you go up, your blood is going to have the effect of going lower and lower. And as you go higher and higher, it's like your blood is going down. So from the relative perspective, it's as if your blood is leaving your brain. So that's why when you get to about 3 G's, you start to pass out for a normal person. Now, if you are out of shape, okay, you actually can handle more G's. Why is that the case? Because when you're out of shape, you have less blood vessels, less capillaries, less blood flow. People who are athletic have a lot of extra blood vessels through their body. The blood flows very quickly. Their heart pumps very efficiently. So what happens is the blood actually leaves faster if you're in shape, which is kind of strange. I know that's strange. So what people do is they wear these G suits and they try to inflate the suits. So the suits, they pump these suits up. They're like air balloons and they pump them up. So what happens is that it's pushing more pressure up so the blood can't come down. So pilots wear these inflatable suits because when they're doing these Gs, when you're at the bottom of a roll here, and we talked about the force of lift is this high and you're down here like this, that you have a centripetal acceleration to the center, and that creates G's, and that causes the blood to leave your brain. So these pilots have to inflate themselves, or they do the hic move, where they go hic, hic, and they kind of hold their chest, and it's the hic move is to tense their muscles to keep the blood from going down. So that's just a little bit about the G's. And so this is important to understand what is a G. The number of G's in this case was 0.88, so that's fine. Now, one more thing about G's, you can have, if you're here and you're actually accelerating down, it's actually much worse because the blood wants to go up, and that can cause something called a red out instead of a blackout. So a red out occurs when you're going up, and the reason that's more deadly is that it bursts your blood vessels. So if you're falling too fast, it's way more dangerous than if you're rising too fast. So just something to think about. Um, all of it's dangerous. Passing out is dangerous too. Like a lot of these stuntmen, when they do, like they cross the Grand Canyon on a rocket or do, stupid things on a motorcycle or whatever to try to do these stunts, that the risk is that they pass out, like because they're going so fast that they might pass out and they may not be able to pull their parachute. So it's not good to pass out, especially when you're operating a vehicle. Now, going back to the space station here. So one of the things to remember is what's confusing about this gravitational term is when we're talking about radius, it's the whole radius from the two centers of mass. Okay, so you have a radius down here, this radius here to this point here, this blue one, that's the one that we're using in the equation to find out the gravitational field. Okay, but in this, so we call that R total. Or if that's little m and big M and little m, we would call that R m big M to little m, whatever. But there's also a radius of the Earth, so that gets confusing. So a lot of times people want to use that as their radius. But that's only true if you're on the surface of the Earth. If you're in a satellite, you have an altitude, and the typical altitude of this satellite is zero point 0.4 times 10 to the 6. So 0.408 megameters. Mega is 10 to the 6. Now, these are just some different G's. On the mean on the Earth is 9.83, 9.80 on Mount Everest, 9.71 in the balloon, 8.7 for the space shuttle, etc. So that space shuttle is very close to the space station example. Now the communication satellite is 0.225. So why is the communication satellite so much lower? The reason is you want to have what's called a geocentric orbit. And why is that important? Well, because if you have a space station, you're zipping around multiple times. I just drew it crashing into the Earth. That's not good. You say you're in orbit, still making it crash into the Earth. But let's just pretend like this orbit doesn't crash into Earth, okay? All right, so it's going in a circle, it's still crashing. Whatever. All right, it's going in a circle, and it's going much faster than the Earth is spinning. So this is why astronauts can see the sun rise and set multiple times, right? So they're zooming across the United States, zooming across Europe, zooming across Asia, zooming across the Pacific, zooming back, so they're going in these really, really, really fast circles. And so they're trying to do that because they're conducting research, and they want to stay close because they want to be able to come back quickly in case there's a problem. A lot of reasons why they do it. There's radiation as you get further out. I mean, it's all kinds of, the further away from Earth you get, is all kinds of problems. So they typically orbit low. Now, to orbit low, like I say, you got to be going faster. So if you want a satellite, let's say that you live here in the United States, and let's say that this is North America. I don't know, just pretend like there's Baja, there's Florida, there's Cuba, whatever. Here's your Caribbean. Okay, and you want a satellite, and you got DirecTV, and your satellite's up here. Okay, let's pretend like that's a satellite. I don't know what that even looks like, but let's pretend like that's a satellite. And you want that satellite to be on a direct line with you all the time. So as you spin, you want the satellite to spin exactly with you in geocentric orbit. Geocentric means, or geosynchronous, sorry, geosynchronous orbit means you want that satellite to move with you exactly, because you want your signal to always be coming as the Earth spins. You don't want the satellite to be zipping around like that space station is going around and around and around. You want that satellite to be creeping along with the Earth. And so to do that, it's at a much higher altitude in kilometers, okay? And so the acceleration of gravity there is much lower, so it can travel slower, right? So that's the idea with that. That's why the communication satellites are so much further away because we want them to be in sync with what we're doing. So you have all of these traffic jams or these traffic lanes, let's just say, at all these different levels of orbit, depending on what people are trying to accomplish. So there's a band out here where all the satellites, our communications are. There's probably a different band for direct TV. They got to share that space. There's a different band for the space station, and they probably have all kinds of channels up in here that they approve for satellites to be in. Okay, so here's a quantitative example of why we feel weightless. Because we talked about this before. If you're still 88% of the surface of the Earth, why do you feel weightless? Well, you are in orbit. Okay, so before this chapter, we said G was constant. Okay, so here's your M2, and mv squared over r is your orbit. And so we said, okay, well, we set up our free body diagram here. So when we want to solve any question, we draw our free body diagram. We draw our Newton's laws here. This is Newton's laws in the y direction. And so mg equals mv squared over r. So v equals the square root of rg. That's showed up everywhere. Even when we're driving in a circle, v is mu square root of mu rg. And we have just, this shows up everywhere. Circular pendulum, v squared over rg, all these different areas, this square root of rg shows up over and over again. But this is not accurate anymore because g is not a constant. So now we have to make that statement more accurate. So how do we make that more accurate? Well, we go back to our gravitational equation here. And so now we're going to still set up the same free body diagram, but we're going to say force of gravity is g m1 m2 over r squared, and that equals m2 v squared over r. When you set those up, what's going to happen is you're going to get g, let's just say big M, let's just make it big M, even though I did m2, m1, m2, g big M, m2 over r squared equals m2 v squared over r. The two M2s drop out, and one of the radiuses drops out, and you end up with V equals the square root of G big M R, V square root of G big M over R. And that's going to be the speed of the satellite. So that's always true. So for the speed of the satellite, that's true. And yeah, that's from now on, that's what we're going to use. And we're going to use this with Kepler's laws too, to derive Kepler's law in a minute, because that's how we're going to find the relationship between the period and the radius. So there's 3 of Kepler's laws, and the last 2 are really more important than the first one, but I'll talk about the first one. The first one is the law of orbits. It says all planets move in an elliptical orbit with the sun at one focus. So all that that means is that you have the sun here on this ellipse here on one of the foci here. So there's another foci over here. And then you have some planet over here orbiting like this. Let's say this is Earth. And then you have your distance here, your radius here to that. Now, there are different parts of the orbit. There's a furthest part, there's a closest part. The furthest part is called the radius of the aphelion, and the closest part is called the radius of the perihelion. All that that means is that this is the furthest point here, this is the closest point here. As you get closer, you speed up and you zip around like this. As you get closer, you speed up, you zip around. And this is how we know that black holes exist, because they see planets doing these strange orbitals. They're going like this, and then they go boom, and they come back, and there's another one that goes here, and it goes boom, and that one comes back, and another one here, boom, and there's just nothing there. So that's how they find the orbit. But we have our minor axis, and we have our major axis. Now, we're going to approximate most of these as circles, but you still need to know the equation in terms of the major axis. Now, the one thing about this is that it looks strange here because the speed is changing, but we're going to learn later that the momentum is going to be conserved. The angular momentum is going to be conserved. So in law number 2, we're talking about the law of areas. So if you have a line that connects a planet to the sun, sweeps out equal areas in the plane of the planet's orbit in equal times. So equal area in equal times. That is the rate of dA dt at which it sweeps out the area is constant. And so I'm not going to do the derivation here because it's not really important. But the idea, what comes of it is that the dA dt equals L, which is angular momentum, over 2m. And that's constant. So in other words, it equals L over 2m. So what that means is that L is constant and angular momentum is conserved. And that comes from Kepler's second law. So as it's moving across, the area that it sweeps out here is going to be equal for equal times. So what happens here is you're further away and there's more area under here, right? But you're going slower. So it's like a narrow, long triangle versus short, fat triangle you see down here. So what would happen is this would be moving faster and you still get the same area from here and here. Now, when we're talking about momentum, you have P perpendicular, P radial, and then you have your P pointing tangential like that at some point in time there. So that's the idea. So the whole point of that is just to say that even when we're not in a circle, angular momentum is conserved. So angular momentum does not have to be in a circle. Now the law of the periods, this one is interesting because the square of the period of any planet is proportional to the cube of the semi-major axis, which is the equivalent to the radius in a circular orbit. Okay, so for a circular orbit, I'm just going to put it like this. So we go back to our square root of gm over r. This is the speed of our satellite, and I'm going to equal that to 2 pi r over t. T is the period. So I square both sides, do some math, and I end up with t squared equals 4 pi squared gm r cubed. Or what happens is when I divide that out, I get t squared over r cubed equals 4 pi squared over gm. And what that means is that that whole term is a constant. And so that's important because when we plot these figures, when we're talking about the galaxy, that number should be the same, or the solar system, that number should be the same. So just something to consider. All the planets in our solar system are 3 times 10 to the minus 24, which I'll show you in a second on a graph. This same thing can be applied for an elliptical orbit. So the semi-major axis is A in this case, so it's just t squared equals 4 pi squared over gm a cubed for an elliptical orbit, which is not a circular orbit. But for a circle, it's the same. So just something to consider. So I have here a spreadsheet that is showing Kepler's laws here, and I'll move this over so we can see it. So you can see that in the actual recording area. But over here, I have the different planets in our solar system over here: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. And I know Pluto has been demoted, but it doesn't really matter because it still follows the same laws. It follows Kepler's laws. So it's an object orbiting, and it has a semi-major axis and a period, and it follows this law. So it's a satellite. Okay, so the idea here is that you have the period in years. So Mercury obviously is really fast, 0.241 of a year. Earth is 1 year. Venus is less, but anything outside of Earth is going slower. So that's important to note. As you get further away, the orbits are slower. But the semi-major axis are here. Doesn't really mean anything per se. But when we do t squared and a cubed, and I divide those two, if I say t squared versus a cubed, you get a constant, which is more or less 3 here. You see this? So that's Kepler's laws. That's the third law, that it's just constant all the time. So there's different ways to interpret this. I can show you each planet plotted. For each planet, it's the same. It's just 3. Or I can actually plot it on a line and show you that as I plot t squared versus a cubed, what does the slope of that line represent? It represents this constant. So that slope, that line is proving Kepler's laws, Kepler's third law right there. And if we just plot t versus a, you get some type of a nonlinear growth here, an exponential graph here. So that doesn't really help us. So that's why you have to do t squared versus a cubed. Another thing I would also say for the AP, if they give you some information like this, like delta y v0t plus 1/2 at squared, they could give you a graph. If you have v initial and you're trying to find a, you could have delta y equals t squared over 2 times a, if I bring that over. So I could have a is delta y t squared over 2, and I can make a graph similar to that, delta y, and I can have t squared over 2 here, and you should get the same thing. The slope should give you 9.8. So just something to consider if you ever see that information on an exam, which they could easily give it to you in a graph. They could be like, what's this? Same thing with pendulum, proving that a period is constant. You could set up some type of a line with, omega is the square root of g over L, and, omega is 2 pi over t equals square root of g over L, and t is, somehow you'll figure it out that that slope of that line is the period, which is constant in simple harmonic motion. So just some things to consider. All right. So again, this is just a manual plot of what we just did, but I think it was more powerful in the Excel. So calculating G at the center of Earth, now we're talking about G. We're not talking about AG. We're not talking about a little g like this from before. We're talking about G, the one we've been talking about. G is different for 3 basic reasons. Earth's mass is not uniformly distributed. Earth is not a sphere. Earth is rotating. So these 3 things affect G, what we measure. We don't measure the actual A of G because we have these things, other things in there distorting it. So how do we find it? Well, we say F of n minus mag, okay, and this arrow is bigger because we have a net force, equals mv squared over r, and F of n, which we measure on Earth, is going to be mg. When you solve all of that over, you get g equals a sub g minus mv squared over r, and that's going to give you the acceleration of g on Earth. Or if we're savvy, right? When we're talking about v, what kind of v are we talking about? Talking about v tangential. And we know that when we go back to our circular motion, we just came out of that rolling chapter, right? That's going to equal r omega, right? So if I have mv squared over r, I just have m r omega squared over r. So I end up with one of those that says r squared omega squared over r. So I end up with just m r omega squared, and that's the centripetal acceleration. So that's why we end up with that v squared over r omega squared. So yeah, you should be able to go back and forth between that, and hopefully between this and the rolling chapter that we can do that. Okay, so now we talk about gravitation inside of the Earth. So what in the world does this picture mean here? Well, what this picture represents is the force of gravity as you approach the Earth. So what is this strange looking shape here? Looks like a volcano or something. So the idea is that as you are outside of the Earth and you approach the Earth, the force of gravity is proportional. I'm going to do the proportional here, not to confuse people again. 1 over r squared. So that force of gravity starts to rise like this. But then once we get inside the Earth, we realize it's not a point mass anymore and everything goes away. But if I went to the other side of the Earth right at the surface, it would decline again as a function of 1 over r squared. And again, it doesn't touch 0, even though I showed it touching 0, but whatever. You get the idea. Proportional to 1 over r squared. Now, what happens when we go inside the Earth? When we go inside the Earth, the force of gravity becomes a linear function of r. So it decreases like this. As you're at the center of the Earth, it goes 0, and then it goes linear increase again as you get away. This is exactly how a spring behaves. So if you got inside of the Earth here, if you're a mass, and you drop that mass, what would happen is it would oscillate back and forth between the Earth, back and forth, just like a spring. So the motion of that object is going to be described by our equations of simple harmonic motion. So x of t is a cosine omega t, right? We take that spring, we're stretching it maximum. The maximum curve, the cosine curve starts here at maximum when I'm stretched, 1 amplitude. And then we know that it travels 1 amplitude and how long? Anybody out there? T over 4. T over 4, 1 amplitude. So it goes 1 amplitude, 1 amplitude, 1 amplitude, 1 amplitude, T over 4, T over 4, T over 4, T over 4, and this is 1 period here. Okay. Vt is going to be the what? Anybody? Negative a omega sine omega t. Now I didn't put the phase shift in here because I'm leaving it simple, but that's going to describe this motion here. Negative, why? Because derivative of cosine is negative sine, and we have the chain rule, which is omega, which comes out here. A of t is just going to be a omega squared, negative a omega squared, cosine omega t. Okay, so the motion of an object inside the Earth, if it oscillated back and forth, would follow these laws of simple harmonic motion. Now, what do these values represent? This represents the amplitude, the max amplitude, okay, the stretch of the spring, or the maximum stretch from here to here. This a omega represents max speed. A omega squared represents maximum acceleration. So just remember these in terms of simple harmonic oscillators because it pertains to this section. So again, this is just saying outside the Earth, F is 1 over r squared. It behaves as if it was a point mass, but inside the Earth is proportional to kr and behaves as a simple harmonic oscillator. Why? Why? Well, we're going to do a little derivation here. So here's the derivation. We're going to talk about intrinsic qualities, intrinsic properties of density. Density functions like temperature are not a function of the total mass, but of the interaction of the mass and the volume. So force of gravity. So it's G, like we said, m total times little m over r squared. And that's no real surprise there. Okay, total of the Earth, but that's on the outside. So we go back to density. Density is mass over volume. And we're going to talk about the density here. I'm going to define some things here that when we go to the surface, we're going to use the term big R when we're going out here to define as we're tunneling into the Earth, little r like this. So we're going in like this, and here's big R, and then there's little r. And as we go in, little r changes. But no matter where I am, if I'm on the inside of the Earth or I'm at the total place, wherever I am, the density is the same. Okay? It's the same. So the density is the mass inside of the Earth over the volume inside the Earth over the mass total over the volume total. That's a constant no matter what. So I can go further with that and say, well, I know that the volume of a cube, or sorry, the volume of a sphere is 4/3 pi r cubed. But inside, I'm talking about 4/3 pi little r cubed, and outside, I'm talking about 4/3 pi big R cubed. Again, they're the same because this density equals this density here, but what's important is now we're parsing it out, and the 4/3 go away, the pi goes away, so you end up with mass inside equals mass total r cubed over big R cubed. And so what happens? Well, let's go back and plug this in. If I want to know the force of gravity inside of the Earth at any one point, it's just G times the mass inside of the Earth, little m over r squared. I plug in the mass inside this relationship, and then the r's reduce down, okay? And you get a constant here. So you get G mass total, little mass constant over big R cubed constant times the radius here. So then you just get kr. So again, you end up with the restorative force is going to be negative kr, and it acts as behaves as a spring, essentially simple harmonic motion, oscillating back and forth. Now, there's a couple ways to define the potential energy. One of them is the work required to take a particle to infinity. And another one is just, we're going to recall that the conservative force is negative du dx. So that comes from our other chapter. So negative du dx is the definition of the conservative force in terms of potential energy. So if I go through this process here, I can say that if I separate these terms and I start to integrate, I get integral of du equals negative f dx. And I'm defining my boundaries here, u initial to u, du, r initial to infinity. Now, I could have put infinity here on u, but I'm just going to substitute that out in a minute. But that equals negative gmm over r squared dr. And when you integrate that, you get negative g big M over r, and then two negatives out here, because you pick up another negative. So then you got three negatives here. And you go ahead and take that to infinity, and you're going to end up with this. Negative g m little m over r, infinity, r initial. And when you plug that in, you get the negative out here, 0, negative g m over r equals u minus uo. But u, which is u final, is 0 at infinity. So that's the important thing here, that at infinity, the potential energy is 0, and the kinetic energy, if we're taking an object out there, is also 0. So if I launch something to infinity from Earth to infinity, that is, if it could make it to infinity, both the potential and the kinetic are 0, because it just like gets there and it just stops. Okay, so the thing to take away from this is that the force is negative du dx, or the work required to take it to infinity. If you can't remember the signs on the AP exam, I know this is a lot of signs here, just remember that the potential energy is negative g m over r. It's negative here, so we're going to start to have negative energy, okay? And so I think you can get there, even if you're not sure about the signs. You need to have it as a negative if you derive that. Now, the other thing to take away from this is that the potential energy depends upon two objects making a connection. So this is not the same thing as field. Field just needed one mass. Potential energy requires two. So just remember that. Now let's talk about escape speed. Before, when we talked about escape speed, what were we talking about? Well, it was pretty simple. Life was simple back then, right? You have all this kinetic energy at the surface, and you're going to turn it all to potential energy here. So 1/2 mv squared equals mgh. So v is the square root of 2gh. That was pretty simple. But now that's not the case. What's going to happen now is that we have to understand that we're looking at this differently now, because we have this continuous function now going off to infinity. What's going to happen here is that if you have an object here, let's say you have a rocket ship and it launches, that at some point you have an initial kinetic and you have an initial potential. Because you have kinetics, because you're talking about here, there's a radius here between the two masses, you have potential, and you have kinetic because you're moving. If you got to infinity, okay, out here, the potential is 0 and the kinetic is 0. So the way that you set this equation up now, you're not going to say that k equals u. You're going to say that my initial potential and my initial kinetic equals 0, because there's nothing, 0, because there's nothing out here. All right, so then that's going to become negative gm big M little m over r plus 1/2 mv squared equals 0. And this is where the sign is important. You see that? If you don't understand the sign, you might be tempted to put it over here, right? And then that doesn't make sense, right? So really the technicalities of this chapter are critical to understand that. So the negative has to be here, and they both have to be on the left side. So the v, escape velocity, is the square root of 2g big M over r. So it's twice the satellite orbit speed to escape. The difference is the satellite orbit speed is going this way. It's a tangential speed going this way, where this one is you're just twice the magnitude trying to get out. So just interesting parallels here. There's similar values that show up over and over again. Now, potential energy of a system of particles is relatively simple. So don't overthink this. It's simply the number of connections between the masses. So if I have mass 1 and mass 2, there's one connection. So the potential energy total of that system, if I put a system around this, there's my system, is just U12. So I would just say G M1 M2 over R12 and add it up. Sorry, negative G, put the negative, please put the negative. Negative G M1 M2 over R12. Okay. But if I go to B, then I have to look at all these. There's more connections. I have to attach all these connections. So I have mass 1, mass 2, mass 2, mass 3, mass 1, mass 3. So then again, you got to add them up separately. This is a scalar. It's easy peasy. You plug it in and you add it up. And you can, sometimes if the radiuses are the same, you can factor out some things, which is good. Or you can, or if the radiuses are different, you can factor out that the masses are the same. Sometimes you can factor out the G and the M in the equation, however you want to do it. But that's it. So now if you had 4, you would have 1, 2, 3, 4, 5, 6 connections, and you would have 1, 2, 3, 4, 5, 6 terms. And think about this again. If you get confused about potential energy, think about it as if you were holding, there's 2 people here, and you're both holding like a bungee cord, right? You need 2 people to hold the bungee cord to feel that potential energy, that elastic potential energy. So uh, not too bad. That's actually one of the better parts of the chapter if you have to think about dealing with potential energy. All right, so now let's go back and revisit orbits because we're going to get into satellite stuff here. So what's going on with between a circular orbit versus an elliptical orbit? Well, we know that the momentum is conserved. We know that the areas swept out are the same, and the relationship between t cubed and r squared is going to be some type of a constant. But what does that mean in terms of eccentricity, which is this letter E? Well, if it's 0, it's a circle. If it's 0.5, it's getting elongated, and then 0.8 would be really elongated. So these are just different ways, if you ever see eccentricity, of just describing how stretched out that is into an ellipse. So before, we talked about that satellite as FG mv squared over r, but now we know that it's G mm over r squared equals mv squared over r. So we're going to do this first step here to define mv squared over r, and this is a derivation. So why did we do this little derivation here? We said mv squared over r equals G mm over r because one of the r's went away. So I'm just going to stop and just hold that off in our thought process for a second. I'll call that equation 1. And I'm going to go back here. So I'm talking about what's the energy of a satellite. Now, we already said that if you have a satellite or a rocket, that you have potential and kinetic at the beginning. Okay? You have potential and kinetic at the beginning. So you have negative G mm over r equals 1/2 mv squared. But we just defined mv squared as G mm over r. So that's going to go in here. So you're going to end up with, and there's a 1/2 still here now. So you're going to have G mm over 2r plus negative G mm over r. Got it? So what does that mean? What's the point of doing that? The point of doing that is to show you that you're essentially saying negative 1 plus 1/2 gives you negative G m little m over 2r is the energy, the total energy of the system, of all of the energy in a circular orbit. So that's the total energy in the system. Total energy in the system. The total U plus the total K. So the kinetic energy is 1/2 mv squared, which is GMM over 2R, which is negative E. So the kinetic energy is negative E. So it's a mirror of the total energy. Okay, so if you do a graph, the total energy is always negative. The potential energy is always negative. The kinetic energy is always positive, right? There's no negatives in the kinetic energy. And the kinetic energy is a mirror of the total energy of the system. Strange. I know it's strange stuff, but that's what it is. Okay. So here's a graph. Let's talk about that. So here is your total energy of the system. Here, we know that's always negative, right? But that kinetic energy is a mirror of that. So let's do kinetic in red because kinetic is motion. So kinetic is your mirror of that. So negative, positive, mirror about the x-axis. Now, potential energy is going to be negative gmm over r. So that's also negative. That's always negative mirror down there. It's not a mirror. That's a negative below that. So that's the idea of that. So strange but true. So that's how we deal with satellites. And that is the end of gravitation. So thanks for watching. I know it was a long video, and I'll talk to you guys soon.